In the present video, we will solve the line balancing problem by ranked positional weight method. Before that, we will discuss the procedure of this method. In this method, step 1 is draw the precedence diagram. Step 2 is for each work element determine the positional weight, and positional weight is the total time on the longest path from the beginning of the operation to last operation of the network. Step 3 is rank the work elements in descending order of ranked positional weight, which is the beginning with the work element with the highest positional weight down to the one with the smallest positional weight. Step 4 is assign the work element to a station. For this, choose the highest RPW element, then select the next one, and moreover continue till cycle time is not violated, and also follow the precedence constraints also. Step 5 is if any unallocated time remains after assignment of a work element, assign the next succeeding ranked work element to the station without violating the precedence relationships and without letting the station time exceed the cycle time. Step 6 is repeat the step 4 and step 5 until all work elements are assigned to the stations. So let's see the one numerical problem for the ranked positional weight method. The output desired is 210 units per day. The factory works in 2 shifts of 7 hours each. The details of assembly task with their duration and precedence requirements are given as follows. So in the table there is given the different work elements and precedence requirements along with the time duration of the each work element. Then determine feasible cycle time, draw precedence diagram. And next question is determine theoretical minimum number of workstations required. And last one is the compute line efficiency, balance delay and smoothness index using RPM method. So let's see the solution. Before that one I have to observe the given data. So in the problem it is given that the output desired is 210 units per day. So number of units are the 210, and also there is given the factory works in 2 shifts of 7 hours each. So here number of shifts per day is 2 and available time per the shift is 7 hours. So total available time per day is the 2 into 7, which is the 14 hours. So let's see the first question is determine feasible cycle time and draw the precedence diagram. So we know that cycle time is the production time divided by required output. So here output or number of units are the 210 and total available time is the 14 hours. So here observe all work elements time is the in the minutes. So we have to convert the total availability time also in the minutes. So 14 hours will become the 14 into 60 minutes. So total availability time is the 14 into 60 and the required output is the 210. Then cycle time will become the 14 into 60 divided by 210, which is equal to the 4 minutes. So next we have to go for the determine the number of workstations by the RPW method. So in the RPW method, step 1 is draw the precedence diagram. So for this one I have to observe the work elements and the precedence relationship. So it is given in the table. So here I have to observe work elements A, B and C. For these 3 elements there is the no immediate precedence. So this is the starting elements. So I have to start with these three work elements and also represent its processing time. For the work element A, so time is the 2.0, and for work element B is the 1.20, and for the work element C 0.80 minutes. So next we have to look for the work element D. It will be start after completion of the work element A. So I have to draw the work element D and its processing time is the 1.2. Next for the E, so it will be start after completion of the work element B and its processing time is the 0.8 minutes. Next for the F will be start immediately after completion of the C. Then I have to draw the work element F after completion of the C along with its processing time is the 0.40. And next is the G. So G will be start after completion of the D and E. So after completion of the D and E, G will be start. Next one is the H. It will be start after completion of the F. So next draw the H. And next one is the I. So I will be start immediately after completion of the G and H. So G and H, after completion of the G and H, it will be start the I. Then I have to draw the work element I after completion of the G and H. And next one is the J. J will be start after completion of the I. So along with its processing time is the 3.2. So this is the precedence diagram. So step 2 is for each work element determine the positional weight. So I have to determine the positional weight for the each work element, and positional weight is the total time on the longest path from the beginning of the operation to last operation of the network. So first I have to determine the positional weight of the work element A. So for this one I have to observe the network diagram. So positional weight is the total time on the longest path. For the A, it will be reached to the last element by the, so this path only. There is only one path is available. So if there is the more than the one path, I have to choose the longest path. But here there is only one path. So here, so longest path is the ADGIJ. Then positional weight is the time on the this path. So positional weight of the work element A is the, so 2 plus 1.2 plus 2 plus 1.6 plus 3.2. It is the 10. So RPW value for the work element A is the 10. So next we have to look for the next work element is the B. For the work element B, so there is the only one path, that is the longest path, and that path is the BEGIJ. Then positional weight of the work element B is the total time on the BEGIJ path. It is the 1.2 plus 0.8 plus 2 plus 1.6 plus 3.2. It is the 8.8. And RPW value for the work element B is the 8.8. So next for the work element C. So for the work element C, so longest path is the, so for this one also there is only one path. So that is the CFHIJ. So positional weight is the 0.8 plus 0.4 plus 1.2 plus 1.6 plus 3.2. It is the 7.2. So RPW value for the work element C is the 7.2. So next for the work element D. So for the work element D, so longest path is the, so DGIJ, and positional weight is the 1.2 plus 2 plus 1.6 plus 3.2. It is the 8. So RPW value for the work element D is the 8. So next element is the E. For the E, longest path is EGIJ. So positional weight is the time duration on this path, that is the 0.8 plus 2 plus 1.6 plus 3.2, it is the 7.6. So RPW value for the work element E is the 7.6. And next for the F, so work element F, so longest path is the FHIJ, and positional weight is the 0.4 plus 1.2 plus 1.6 plus 3.2, it is the 6.4. So RPW value for the work element F is the 6.4. And next is the G. So for the work element G, so longest path is GIJ, and its positional weight is the 2 plus 1.6 plus 3.2, it is the 6.8. RPW value for the work element G is the 6.8. And next for the work element H, for the work element H, so longest path is HIJ, and its positional weight is the 1.2 plus 1.6 plus 3.2, it is the 6. So RPW value for the work element H is the 6. And next for the work element I, for the work element I, so there is only one path, that is the I to J. So and its positional weight is the 1.6 plus 3.2, it is the 4.8. And next for the positional weight of the work element J, so it is the 3.2. So next we will go for the step 3. Step 3 is the rank the work element in descending order of ranked positional weight. It is the beginning with the work element with the highest positional weight down to the one with the smallest positional weight. So first I have to give the ranks for the work elements according to their RPW value. So highest RPW value is the 10 for the work element A, and next highest value is the 8.8 for the work element B, and next highest value is the 8 for the work element B, so rank 3 for the work element D, and next highest RPW value is the 7.6 for the work element E, so I have to give the rank 4 for the work element E, and next highest value is the 7.2 for the work element C, so it is the rank 5, and next highest RPW value is the 6.8 for the work element G, so for the work element G, rank is the 6. Next highest value is the 6.4 for the work element F, so it is the rank 7. Next highest value is the 6 for the work element H, and its rank is the 8. And next highest value is the 4.8 for the work element I, and its rank is the 9. And there is the only one work element, that is the J, and its rank is the 10. So once again we have to rearrange the work elements according to their ranks. So first I have to give the position, highest position for the rank wise. So I have to rearrange. So first rank is the for the work element A, so it is the first. So next to second one is the B, next to third one is the D, and next to fourth one is the E, and next to fifth one is the C, so C, and next one is the 6 for the G, so G, and next to 7 is the for the F, so next element is the F, and next one is the 8, so for the element H, so element H, next to ninth one is the I, so ninth one is the I, and last one is the J, so last one is the J. So I have to rearrange the work element according to their ranks. Next we will go for the step 4. Assign the work element to a station. Choose the highest RPW element, then select the next one. Continue till cycle time is not violated and follow the precedence constraints also. Parallelly we will solve the step 5 and step 6 also. So for this one, we have to draw the tabular column. So like this, with the columns of workstation, work element, time, RPW, cycle time and the ideal time. So first we have to assign the work elements to a stations. First we have to start with the station 1 and first element is the element A. So and its cycle time is the 4 and its processing time is the 2. Then ideal time is the 4 minus 2 which is the 2. So now ideal time or available time is the 2 and next element in the station 1 is the B and its time is the 1.2. So we can be add the work element B in the station 1. Then ideal time will become the 4 minus 2 minus 1.2 which is the 0.8. And next here ideal time is the 0.8 after completion of the work element B in the station 1. And next work element is the D and its processing time is the 1.2 but available time is the 0.8 only. Then we can't able to add the work element D in the station 1. So have to close the station 1 with the work elements of the A and B and its ideal time is the 0.8. So next we have to start with the second station with work element of the D. Then ideal time is the 4 minus processing time is 1.2, so it is the 2.8. And next work element is the E. Its processing time is 0.8 and available time is the 2.8. So we can be add the work element E in the second workstation. Then ideal time after adding the work element E in the second station, that is the 4 minus 1.2 minus 0.8 which is the 2. Next work element is the C and its processing time is the 0.8 and available time is the 2. So we can be add the work element C in the second workstation. So and ideal time after the adding the work element C in the second station, that is 4 minus 1.2 minus 0.8 minus 0.8. So it is the 1.2. So next we will move to the work element G and its processing time is the 2. But here observe availability of the ideal time is 1.2 but processing time required for the work element G is 2. In this regard we can't able to add the work element G in the station 2. So now I have to close the station 2 with the work elements of the D, E, C. So next we have to start the next workstation. So that is the third station with the work element of G. So now ideal time will become the 4 minus 2 which is the 2. And next work element is the F. Its time is the 0.4 and ideal time or available time is the 2 minutes. So we can be add the work element F in the third station. Then ideal time will become the 4 minus 2 minus 0.4 which is the 1.6. Next work element is the H and its time is the processing time is 1.2 and here ideal time or available time is the 1.6. So we can add the work element H in the third workstation. Then ideal time after the adding the work element H in the third station. So ideal time will become the 4 minus 2 minus 0.4 minus 1.2, it is the 0.4. And next work element is the I. Its processing time is 1.6 but our available time is the only 0.4. So in this regard we can't able to add the work element I in the station 3. So now I have to close the station 3 with work elements of G, F, H and ideal time is the 0.4. So next we have to start the new station, that is the station 4 with the work element of the I. So its processing time 1.6, cycle time is the 4, then ideal time is the 4 minus 1.6, that is the 2.4. Next work element is the 3.2 but here ideal time is only 2.4. So we can't able to add the work element J in the fourth workstation. Then I have to close the fourth workstation with only one element, that is the I, and its ideal time is the 2.4. So next we have to start the new workstation. So workstation number 5 with the work element J, and processing time is 3.2, cycle time is the 4. So ideal time is the 0.8. So this is the assignment of the work element to the respective stations. So here there is the 5 stations are possible. So first station is with the elements of A and B, ideal time is the 0.8. Second station is having the elements of D, E, C, and ideal time is the 1.2. And third station with the work elements of G, F, H, and ideal time is the 0.4. And fourth station which is having the only one element, that is the I, ideal time is 2.4. Next to fifth station is also having the only one element, that is the J, and ideal time is the 0.8. So this is the assignment of the works to the work elements to the stations. So next we calculate the line efficiency. We know line efficiency is the sum of task times divided by actual number of workstations divided by workstation cycle time. So there is the sum of task times is nothing but time duration for the all the work elements, and number of workstations are there is the 5 workstations, and workstation cycle time is the 4. Then we have to substitute all values in the efficiency. Then efficiency equal to 2 plus 1.2 plus 0.8 plus 1.2 plus 0.8 plus 0.4 plus 2 plus 1.2 plus 1.6 plus 3.2 divided by 5 into 4. This value is 0.72, which is the 72%. So next we determine the balance delay, which is the 1 minus efficiency. So 1 minus 0.72, that is the 0.28, which is the 28%. So next we calculate the smoothness index, which is the square root of summation of I equal to 1 to n maximum station time minus station time of ith station whole square. So it is nothing but square root of summation of ideal time square of the each station, that is the root of 0.8 square plus 1.2 square plus 0.4 square plus 2.4 square plus 0.8 square. So its value is 2.939, and this is the solution, and thank you.